Fluid dynamics tutorial. Turbulent flow over a backwards-facing step. Flow over backwards-facing steps are classic computational fluid dynamics test problems, and are often used for validation of simulation codes. This test case consists of studying how the flow field reacts to a sudden expansion in a channel. The expansion will cause a break in the flow, and a recirculation or separation zone will form. To validate the simulation, the resulting length of the recirculation zone is compared with the experimental results of Pitz and Daily. In this example, the stationary incompressible Navier-Stokes equations are used to model the fluid, with simulation parameters corresponding to a Reynolds number of 18,000. The flow is therefore fully turbulent, whereby a turbulence model closure must also be applied. Here the standard K-Epsilon turbulence model is used, which is available with the OpenFOAM CFD solver. This tutorial can be run by selecting Model Examples and Tutorials, Fluid Dynamics, Turbulent Flow over a Backwards-Facing Step, from the File menu, and followed along with the step-by-step instructions in the user's guide. To start a new model, click the New Model toolbar button, or select New Model from the File menu. In this example, variations in the z direction are assumed to be negligible, which enables using a planar 2D approximation and saving computational cost compared to a full 3D simulation. Select the 2D radio button. Select the Navier-Stokes equations physics mode from the Select Physics drop-down menu. Press OK to finish the physics mode selection. Geometry mode. The backwards-facing step geometry features a slightly tapered outflow region, which is easiest to create by directly specifying a polygon by coordinates. Select Create Object, Polygon from the Geometry menu. Enter the following data into the point coordinates table. Press OK to finish and close the dialog box. The dimensions are here given in meters. However, note that the toolbox works with any unit system, and it is up to the user to choose consistent units for geometry dimensions, material, equation, and boundary coefficients. Grid mode. Switch to grid mode by clicking on the corresponding mode toolbar button. For turbulent flows, it is particularly important to ensure a fine resolution near walls, due to viscous boundary layers which feature steep gradients. The default grid will be too coarse to ensure an accurate solution. To create a finer grid, enter 0.002 into the grid size edit field, and press the Generate button. Equation mode. Switch to equation mode by clicking on the corresponding mode toolbar button. Since the fluid is air, set the density to 1.293, and viscosity to 18.1 E-6. Press OK to finish and close the dialog box. Boundary mode. Switch to boundary mode by clicking on the corresponding mode toolbar button. In the Boundary Settings dialog box, first select all boundaries, except for the right outflow and left inflow, and choose the wall no-slip boundary condition from the drop-down menu. Select the leftmost boundary, and choose the inlet velocity boundary condition from the drop-down menu. Enter 10 in the edit field for the x velocity coefficient U0. Finally select the right outflow boundary, and select the outflow pressure boundary condition from the drop-down menu. Finish the boundary condition specification by clicking the OK button. Solve mode. Now that the problem has been defined, press the Solve Mode toolbar button to switch to Solve mode. Instead of using the built-in multiphysics solver, the external and dedicated CFD solver, OpenFOAM, will be used to solve this flow problem. Press the OpenFOAM button to open the OpenFOAM Solver Settings and Control Panel dialog box, and set the stopping criteria to 1E-4. Select the K-Epsilon turbulence model from the corresponding drop-down menu, and press the Edit button to open a dialog box where the turbulence inlet quantities can be prescribed. The K and epsilon inlet values can either be estimated from a given turbulence intensity and length scale, or as is done here, prescribed directly if the quantities are known. Enter 0.375 into the edit field for the turbulent kinetic energy, 14.855 into the edit field for the turbulent dissipation rate, and press OK. Advanced users can also use the edit functionality to view, fine-tune, and modify OpenFOAM dictionaries, as well as export case files for running OpenFOAM simulations separately. Press the Solve button to start the OpenFOAM solver. The solver control panel will automatically change to show the convergence process for the flow variables. During the solution process, one can switch between the convergence tab and the solver output log. The solver will stop when the residuals for all of the flow variables are below the stopping criteria, or the maximum number of iterations has been reached. Post-processing mode. After the solver has finished, the toolbox will automatically switch to post-processing mode, and show the resulting velocity field. One can see that a recirculation zone has formed after the step. To visualize the recirculation zone more clearly, open the Post-Processing Settings dialog box, and enter the expression for the normalized recirculation zone length into the surface plot expression edit field. The arrow plot option can also be turned on to help visualize the flow field. The resulting plot shows a recirculation zone length of about 6.25 normalized length units, which is quite close to the reference length of 6.4. The tutorial is now complete, and the model can be saved as a binary file, exported as a MATLAB M script file, or a GUI playback file.